Tonight, I'm very pleased to introduce, for this week's lectures, co-sponsored with the Princeton University Press, we are hosting Professor Peter Ward of the University of Wisconsin. Professor Ward's lecture tonight is part of the Stafford Little Lecture Series, and as I said, is co-sponsored by the press. The series was made possible by a bequest from Henry Stafford Little of the class of 1844. Mr. Little was a lawyer and was active in New Jersey politics and was the first president of the New York and Long Branch Railroad Company. Stafford Little first suggested that Grover Cleveland be invited to give a lecture every year on such topics as he might be disposed to give every year. Mr. Cleveland was the Stafford Little lecturer until his death in 1908. After that, the Committee on Public Lectures expressed an intent to use the fund to address topics in the general area of the social sciences. And over the years, the social sciences have been interpreted to mean a lot of different things, and past lecturers have included Teddy Roosevelt, Albert Einstein on the meaning of relativity, Henry Stimson, Arnold Schoenberg, and Thurgood Marshall. So as you can see, this is a very broad lecture series. Tonight we have Professor Peter Ward, who's been active in paleontology, biology, and more recently astrobiology for more than 30 years. He's published more than 120 scientific papers dealing with paleontological, zoological, and astronomical topics. He's the acknowledged expert on mass extinctions and the role of extraterrestrial impacts on Earth. In that capacity, he's funded by NASA for mission planning on Mars. He's nearly unique in being a cutting-edge scientist as well as a tireless popularizer of science for the public. He's published 14 books to date on a remarkable range of subjects, including mass extinctions, astrobiology. Relevant tonight are several books I'll just mention: Rare Earth, Why Complex Life is Uncommon in the Universe. That was featured on Nightline, was one of the 10 most important science books of 2001 as described by Discovery Magazine. And he has several new books. Recently he has Out of Thin Air, Dinosaurs, Birds, and Earth's Ancient Atmosphere. And he's currently working on, or is about to release, Under a Newly Green Sky, The Global Warming, Mass Extinctions. And that was recently abstracted in the October issue of Scientific American. So if you're interested, you should go to the recycling bin, get out the October issue, and read that. And finally, some of you may know him as a regular on the Art Bell Coast to Coast radio program, as well as on National Public Radio's Science Friday with Ira Flato. So I think that introduction was somewhat longer than he wanted it to be, but nonetheless, I'm very honored to give you Professor Peter Ward.
Tireless. Yeah. Thank you, and thank you for all coming out on this cool evening. I had been reading all about the press about global warming, and 70-degree Princeton brought no coat, of course. And what happened? Got really cold all of a sudden. Thank you, too, for the great introduction. And have I been fired? I'm at the University of Washington, but if Wisconsin wants me, I'll go. It's all right. It's okay.
Wednesday and Thursday, we'll say Washington.
Well, I may not have a job by then. I don't know. We'll see. Uh-oh. It's really fun to do these. Someone asked me, how about these lights? Do you get nervous giving these talks? And a long time ago, I used to get nervous giving these talks. And then I realized that this is really pretty fun. And at first I used to think that I was going to places where there just was nothing else to do, or why would anybody else come out on a cold night, come to see some pointy-headed PowerPoint-giving professor. But increasingly, I embrace communities, and I try to get to as many talks as I can myself. I think, unfortunately, what I will talk about tonight is talking to the converted, because I think our major challenge in this country is science literacy and getting to those who are not available or willing, for whatever reason, to come to talks like this, or any talk where you have to expand yourself. And the reason I wanted to give these talks was that recently I've been involved in Seattle with debates with those who promote intelligent design. Seattle, to its shame, has the Discovery Institute, which is the head of the discovery or the intelligent design movement in America. Now, how that liberal and well-educated city got Discovery Institute, we don't know. But these three lecturers are a direct result of my two interactions with them. And I want to do three lectures. Tonight I want to talk about the ghost of Christmas past, or death, mass extinction, and I've wore all my black clothes accordingly. But tomorrow I have my Miami Beach white suit, and so we'll go into hope and hopefulness over the next 2 lectures. So the Ghost of Christmas Past tonight, I want to talk about creationism and science briefly, and especially talk about intelligent design. I want to really think then on the history of mass extinctions and the history of life and ask, is there a relationship really between what the idea of intelligent design promotes and their view of the universe? How can it really explain what we see in the rock record? What is the history of life on this planet? And over the next 2 lectures then go into something about the future of life on this planet, as best we can understand from what is a really exciting and new field called astrobiology. Well, last April 26th, the Seattle Times, the biggest paper, sported a one-night knockdown, drag-out mud wrestling tournament between Dr. Stephen Meyer or Dr. Peter Ward, or so it was pushed on the local radio shows that we would have a debate over intelligent design. Meyer is a trained paleontologist who has now become one of their most slick purveyors of this snake oil, and he's extremely good. He's likable, personable. You get in a room with him, he knows everything. And what I should have known, and didn't at the time, was he's also a trained debater. So I wandered up to this hall. I had my 9-year-old in tow and my wife. They dropped me off. And we see this crowd outside. Well, they're charging $5 to $10 a pop, so I figured 25 people are going to show up. It's a beautiful summer night, and 1,000 people are there. 200 of them had been bussed in by the Discovery Institute, and they all sat in the front. It went on for an hour. It was a very interesting exercise, and it was interesting in that I'm a scientist and I deal in the rules of science, and somehow stupidly expected that because this was to be a debate over what they called science, that there would be rules of science. And early on in the debate, or the so-called debate, I suggested this to him. I said, my friend, I want you to give to me the hypothesis that you would put forward that, if failed, would cause you to reject intelligent design. And I'll give you mine, equal opportunity. I'm an evolutionist, but I'm a paleontologist. If we go out and find nice Cretaceous rocks, and we can tell that in these Cretaceous rocks there are not only a scapula of a T-Rex, but a Homo sapiens skull, and there's been nothing messed around with, that skull is of that age, and we can date everything, I quit. At least I'm going to reject evolution as I know it in so many parts of it. So what's yours? But he won't answer that, of course, because there isn't one. There is no scientific hypothesis that can discredit or cause you to eliminate this idea called intelligent design, because one does not exist. And yet the debate went on for another however long, and I must say that he actually completely kicked my butt. At the end of this, I had emails. I had emails from his supporters castigating me for being so mean to him. But I had many more emails from the evolutionary supporters saying, you didn't kick his butt enough, or at all, depending on who the supporter was. And here's the real problem with debating these people, and why about a third of my faculty prior to this said, don't do it. Do not get on the stage with these people. You are simply giving them credibility by appearing with them. Ignore them, just as we've ignored them. Well, my point of view is we're in the trouble we are in this country along the lines of creationism and intelligent design because we have ignored them. But you can't win their debates, at least not at that moment. But what you can do is perhaps get people to think after the fact, away from the he won, he didn't, who's better, this or whatever, the debating tricks, with some thoughtful things. And I think our country needs thoughtfulness more now than any time since at least Bush was elected. Well, there's another part of this, and I expose myself to you completely. Never has there been a more exposed speaker anywhere. I have no shame whatsoever. I've cut it off here at least, so we don't have to deal with some of the other anatomical features. But this is me. This is me. This could be the fate of some of you. This is a field geologist who fell off too many rocks. So this gets stuck in me. It's here right now. I got on a plane for the first time. I'm in Seattle 2 days ago. I go up to the metal detector. I mean, it didn't just go ding, ding, ding. It goes honk, 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 and big red lights go around, and these guys come running out, and they grab you, and they take you back, and they put you in your own room. And I said, I'm filled with metal. And they said, well, sure you are. Start taking your clothes off. Go everywhere, and they're doing all this stuff, and they finally let you out, and they say, well, that bomb sure is well supported and hidden, so you can go on the airplane. So this is the new world. Now, I don't show this for, why am I showing this? I'm showing this because, first of all, had this been, say, 100 years ago, 1,000 years ago, 10,000, 100,000 years ago, I would have been dead long before I got to this point. Because of the lack of mobility out on an African veldt, natural selection, I'm out of the gene pool. But the reason I also show this is there was a second nastiness. You know, we used to be on all fours down like this, and our intestines were all tucked in. And then we all went upright. And when we upright, you know, all that stuff in here, it's got a whole new orientation. It's a really bad design to go from on forward and then up. Because in a short period of time, evolution takes a long time to do some fundamental stuff. In a short period of time, some of us humans start getting like bulging outward. It used to hang down, but now it does other things. And there's some other even worse aspects of it. And on this night, I was damn near dead. At least I would have died. And I was surgically cut open from here to here because of a really bad design of a colon, large intestine, small intestine. And my surgeon, when I came out, said, you know, it's really a bad design. I'll tell you how this should have been designed. We should have done this, and you tuck this around here, and that fold really is a mess, and this is terrible. Well, that's why I missed the lecture in November. But our bodies are filled with these things, filled with these problems, filled with this terrible design. Now, evolution is compromise, and they're bad compromises, and we're short-lived creatures. If I were to design us, I could do a much better job, I think. Any designer would have done a much better job. But natural selection doesn't really care about we silverbacks. You know, we're out of the gene pool. We die, and so what? Because evolution drives it. And tonight I want to talk about some aspects of life and death and the history of our planet that show that evolution is a series of compromises. Creationism in this country has a sordid history. Evolution was a crime in 3 states in the 20s, the famous monkey trial. We have the ups and downs. And the one I like finally is the 2005 Dover decision. If you haven't read this decision, you should. I think every teacher should read it to various middle school, high school certainly, because this was a Republican-appointed judge who was so outraged by the nonsense that the Discovery Institute was putting forward as to why we should teach intelligent design rather than evolution in high schools. It's amazing. And yet, it still continues. Currently, we teach phony evidence against evolution in the name of critical thinking. Our president, teach the controversy. We have some really smart people, and this is one of the smartest. This is, go back. William Dembski, who is really the head of the science behind intelligent design, or at least he calls it science, and he's arguing that we have to compare probabilities, and his arguments are that certain things are improbable. But I think any of us who have worked on the rock record, anybody who's been out and studied sedimentary rocks and really gets a feel for how long time is, geological time, I mean, it's something that is very, very difficult, I think, for anybody to comprehend 1,000,000 years. So the wedge strategy right now at the Discovery Institute is this: to defeat scientific materialism and its destructive moral, cultural, and political legacies. Amen. Replace materialist explanations with theistic understanding. See intelligent design theory as the dominant perspective in science. It's really pseudoscience. And I believe that all of us, in our own way, in some way, must understand that this is a danger, that we do have to get on stages with them, and if they kick our butts, that's just one tiny battle. It's a war, folks. So the stakes to me are the following, and this is what I presented in my talk in Seattle on that night, as to be the most important reason that we must continue. What does it say to our young people if we say that some problems are just too difficult? That it's improbable that this could be done by natural means. In fact, it's so difficult that only God could have done it, because these guys say in a coy way, oh no, the designer is not God, but certainly they believe it's God. So what sort of message is that? But to me, it's the scariest aspect about our country now is, what do we produce? Who's the best car maker on the planet? Toyota. What does America produce? What we produce best are the people in this room, the brains in this room, and the young people in this room. And if we do not continue to produce the best engineers and scientists, we as a country and an economy are in for dark ages. And yet I find that intelligent design and pseudoscience and what we see throughout is simply an attack upon that. Let's look at, I think, one of the scariest metrics of all, 2004. This is the production of engineers in the United States, India, and China. So this is what we're dealing with now, a global competition. And we are going to have to deal with this as a nation. Intelligent design is one way to go backwards. So that's the context of why I began thinking and debating and dealing with these people. And tonight I want to think about one aspect of it. I want to bring in astrobiology and look a bit about the nature of our planet, how it was produced through time, how it evolved, and how life upon it evolved. And also think about the nature of astrobiology. Is there any relationship to creationism? And I think that there are scientific discoveries, inferences from astrobiology that can be very useful in understanding and bringing down some of the pseudoscience. So what I see is that some of the creationists suggest that the Earth is a unique abode for life. There's a book called Perfect Planet, and there are many of these unique Earth ideas. Only the Earth has life. And secondly, there can only be one kind of life, and that was produced by God, and that is Earth life. So in the next 3 nights, we want to look at both of these. Let's see how unique the Earth is. It isn't. And let's see if there's any other possible way that life on this planet could happen. But before we do that, I want to show you that our planet itself is a highly imperfect planet. That just like my hip, and just like this intestine of mine, badly designed. And that as a planet, as an abode for life, we are seeing it running down. The Earth is old. As an abode for life, it's old. It's in old age. The odd thing is that we complex life have appeared at the very end of the Earth as a habitable planet. The first animals on this planet appeared 500 million years ago. The last animals on this planet are likely to disappear 500 million years from now. We are halfway through the age of animals. And the age of animals is an Oreo between 2 great bacterial worlds. And as habitability starts going down for complex animals, the Earth is going to change into something very, very different from what it is today. Astrobiology tells us and gives us these predictions, and that will be one of the things we'll talk about starting tomorrow. So some hard questions, though, that I'm going to have to deal with, and I find running up against were very difficult. What is success? What is success for a species? And here's some of the struggles I'm running into. Is success longevity? If it's an old age person, we look at 100-year-old people and say they're successful. Or is it something else? If it's a species, is it the geological age? The chambered nautilus, the first animal I worked on, can be tracked out back 500 million years. But some cyanobacteria are probably 3 billion years in age. Are they successful because of the longevity? Or are they successful perhaps because of abundance? Or are they successful because of the number of new species they produce? And what about complexity? Is complex advanced and simple not? We'll tell that to the bacteria, which really are the largest biomass on this planet and run things for we animals in ways that we're only now beginning to understand. And so success really becomes somewhat qualitative, and yet when you really want to attack ideas, you need to come up with something about success or lack of success. It's very difficult to do. So falsification then of the intelligent design idea about the universe, I think, is that if we find other habitable planets, and if we can find or build life that's different, that can demonstrate that there could be other forms of chemical life, then I think we can falsify some of these ideas about a designed universe, a designed life, a designed planet. And that's my hope here, is to at least cast some doubt on design arguments. Well, astrobiology is the study of life in the cosmos, not just on this planet, but on all planets. And I think all of us who do this fully believe that there will be other life, other kinds of life, lots of other life. There's 400 billion stars in our galaxy. There are billions of galaxies. I think it'd be very foolish to say that we are unique. We can't prove that. As yet, we found no other life than Earth life. But we are certainly finding every year more and more planets. And we are certainly, through many different lines of evidence, including many by those at this university, understanding that habitable planets probably aren't going to be rare at all. We want to find specific and important principles of astrobiology, and the ones I want to present tonight, my own work, come from looking at the past record of major events on this planet, events which probably had an astrobiological connotation. So my work has shown, and we've known for a long time, that life is challenged. Obviously, an individual's life is challenged, but the aggregate number of species on this planet can be challenged and extinguished by external threats. And the threats can be broken up into those of extrinsic, and of these we think impact of a comet or an asteroid or the explosion of a nearby supernova, as well as intrinsic, those from our own planet. Atmospheric change, climate change. The role of plate tectonics in moving continents around has shown us that we have great changes in the atmosphere. And so what astrobiology is trying to do now is trying to understand how many of the threats or how many of the events of the past have been extrinsic versus how many are intrinsic, and what are these? It's funny, too, that if we go back and try to understand the history of understanding threats, we don't have to go very far back in the history of science to see that this whole concept of extinction, the removal of species, only really dates back to about 1800. This is the first diagram of what was thought to be an extinct animal. This is by the great Baron Georges Cuvier, the father of comparative anatomy. And Cuvier had amassed great bones. If you've been to the Jardin des Plantes in France, in Paris, and the Garden of Luxembourg, there's this beautiful old museum anteroom with all his bones still in it. You know, we don't do stuff like that anymore. Hundreds of skeletons, all dusty and dirty, all stuck up. And one of them is this one. Cuvier had received bones from all over the world. He put them together, and he really knew the nature of the world's mammals. At that time, France, an imperial power, England, an imperial power, all the Europeans were moving across the planet, bringing back treasures from their newly conquered lands, and bones came with them. And Cuvier was given these bones. He said, I've never seen these bones. This is an animal which is now extinct. And it's no, I think, coincidence that one of the largest animals that ever lived becomes the first as a proof of extinction. It's hard to hide an animal that big anywhere. In 1800, they'd done enough searching that you couldn't hide any of these guys. And this is why he said this is a proof. Extinction has taken place. This is so ironic to me now. We live in a world where we say hundreds, perhaps thousands of species go extinct every year. At 1800, here's a great giant saying extinction is a process. Darwin certainly knew of this work. And by the time Darwin and his great theory came about, it was understood that lots of things had gone extinct. In fact, extinction became a process of huge importance to the then burgeoning and growing field of geology. How could you date sedimentary rocks except by the fossils within them? And how could those fossils be any good or any use to anybody unless they disappeared every once in a while? And in fact, it was the disappearance of species that led to this diagram in 1860. This is a wonderful diagram in the history of science, not just for we geologists, because it's here that we get these iconic terms, Paleozoic, Mesozoic, and Cenozoic. And these are the three great divisions of the rock record that led Phillips and Darwin and those around them for the first time to break up these piles of rocks into aggregates of time. And they did it because Phillips and Darwin knew enough about the fossil record in 1860 to recognize that the abundance of fossils was variable and that there were two periods of enormous crashes. They had no idea how many years ago this was. There was no way of getting any quantitative estimate of years ago. But in relative terms, they knew that the fossil record started from nothing, and then we had trilobites and some brachiopods, corals, bryozoans, started to see vertebrates, and then we had the gigantic crash. And then all kinds of new stuff appears. Dinosaurs, ammonites, lots of new kinds of clams, crash. Mammals, modern clams, echinoderms, forams. They saw this pattern. And what's interesting about this, it is not only the first document that gives us time, it also is the first history of biodiversity on the planet. From this diagram, it appears that we seem to have more species on the planet now than any time in the past. And this, too, has been borne out. Here's now a modern view of this particular graph turned around 600 million years ago. Here's the geological periods we have now, Cambrian through Permian, a big crash, Triassic, Jurassic, Cretaceous, a crash, and the modern day. This is Jack Zukowski's graph of marine species. And it would suggest there's more animals on our planet now than any time in the past. But what caused those crashes? Uniformitarianism was the great theory that you could not have had things in the past that you couldn't see today. So how could you have made so many of those species disappear so quickly? Well, it wasn't until really this century, halfway through the century, that people started thinking maybe it's not of the Earth, it's outside the Earth. Here's a picture of a supernova, the Crab Nebula. And in the 1960s, a great German paleontologist named Adolf Schindewolf said the supernova exploding near the Earth may have caused these great diebacks in species. The diversity of the planet dropped because of radiation hitting our planet. But by far the most interesting of all the extinctions was the one that caused the end of the dinosaurs. And it was this one that really started pushing forward an idea that not just outside the Earth, but of the Earth itself, were competing hypotheses to be examined. Was it a volcanic eruption? Like in every movie I ever saw as a kid, there were all these great dinosaur movies. You always knew it was near the end of the movie because the volcano exploded, right? And some T-Rex gets and burned up. The movie's over. So they're with the dinosaurs. Sure, why not? Volcanoes. But other stuff, the seas go up and down, climate change, and finally this one, impact. And we want to talk a little bit about this because from 1980 to the present day, impact has been the dominant theme, paradigm for understanding past mass extinction. So if any creator created the universe, that's some bad juju they put when they put all those asteroids and comets up there. So let's look at that. Well, this had to be one of the greatest of all science stories of the 1900s. It had everything: dinosaurs, death, rocks from space, dueling scientists, reputations raised, trashed. I mean, people really began to hate each other. In 1981, I was working at Davis, California. Louis Alvarez, the great Nobel Prize winner, and his son Walter were close by Berkeley. And I had just come up with a theoretical study suggesting that the ammonites, the group I worked on, disappeared suddenly. Boy, I was invited over, I was taken to dinner, and when a Nobel Prize winner takes you to dinner, it's just so great. You know, you glow. And the next year I went out and actually did some digging and suggested that it was gradual, not rapid. Ooh. His adversary, Clemens at Berkeley, invited me over and took me to dinner, but he wasn't a Nobel Prize winner. And the Alvarezes wouldn't even go to the talks. And if it wasn't what they wanted to hear, they weren't going to hear it. And the whole society just sort of split. And it got so nasty, but it was so wonderful. So all of that started here. This is the hillside in Italy. This is Alessandro Montanari, a Walter Alvarez grad student on the so-called famous Gubbio KT boundary site. And we see in this particular slide that we have these white rocks by his head and sort of pink rocks above and pink rocks below. And Alessandro was involved with Walter in studying these rocks. And the question was, how long did it take to go from the white to the pink? What's more interesting than simply white to pink is the fact that the white rocks below had lots and lots of fossils. In this particular case, they're not dinosaurs, they're planktonic foraminifera, but over 50 species. And the rocks right above had one species. And it was one species of a tiny little really non-ornamented guy and lots of species below, you have a great scientist, Gerda Keller, who studied these sequences at Princeton for 20 years, and she would attest that this is an amazing changeover. So many species below, so few above. Well, back in 80, they were pretty amazed there too. And Alvarez has made a prediction. They said, we think that if you go to any of these so-called KT boundary sites, here's my laser pointer, any of these boundary sites, see, I can still jump with it though. They work. We will find the same thing happen, lots of species and no species. And they were right. And I want to walk through this because I think this really gives us an indication of how great this Alvarez theory was. Who's got a laser pointer? I was told someone to have one in the front row, second row. That's a good prediction. Thank you. I have a really good friend named Don Brownlee. He's the Stardust PI. We wrote a couple of books together, but Don also loves gadgets more than anybody on the planet. And he bought an industrial laser pointer. So I'm in his office. And he said, you see that street sign? I said, what street sign? He said, the 1.5 mile away? I said, sure, watch. Zap! The whole thing lights up, right? Of course, meanwhile, some plane. So Don isn't allowed at these talks because he aims it the wrong way. Okay, here we have all this white stuff. It's chalk. We around here don't really get chalk because we don't have it so much in North America. On the West Coast, we have none of it. This is composed about 98% of the skeletons of single-celled planktonic plants, coccolithophorids. In the old days I used to work, we had chalkboards. And you would take a piece of chalk and rub it across, and there would be millions of poor, dead, desecrated skeletons left behind. You know, chalk was a terrible thing to work with. I always thought it was terrible. You're a tough audience. So we have all this white stuff, and then it just stops. And then we have a very thin red layer. It's 1 millimeter thick, oxidized, and it all goes black. And I think this is the best indication visually of what an impact extinction would have been. Because we have a normal marine bottom. This is probably about 100 meters thick. It was rich in animals on the bottom, in the water above it. And the plankton was everywhere. And all these skeletons fall down. And then something happens, the emplacement of a 1 millimeter layer. And then you got black rock with no white in it. And at the very top again, it goes white again. Now we can interpret this. We have a Cretaceous world that's working fine. Everything's perfect. And nobody is dying. And on one day, we get the emplacement of a thin red layer, and then we get lots of rock falling down with a complete absence of plankton, because the plankton is almost virtually wiped out. Some 10,000 years later, it starts going white again, because we have a re-evolution and a repopulation of the oceans. An impact extinction is like an earthquake. This whole city has been knocked down. Nobody lives in it for a while. It starts getting rebuilt. And by the top of this picture, we're back. Except it's not the same city anymore. San Francisco didn't come back to San Francisco before. It came back a whole different kind of city afterwards. So an impact is like that. And it's really fast. The evidence is of several types. We have the accumulation of iridium. Iridium is a platinum group element that is extremely rare on Earth, but is very common. We had bits of quartz that showed shock lamellae. These can only take place under enormous pressures, not earthly pressures, extraterrestrial impact pressures, or nuclear weapons will produce these too. So the quartz underneath a bomb blast or an impact becomes shocked. The iridium itself is, again, significant in that it's rare in crustal rocks, and we can, from the amount of iridium, make some estimates about the size of the KP impactor, and the Alvarez's did 10 kilometers diameter. Now, about the time that this was happening, I was doing a couple things at once. I was also working on the chambered Nautilus, but the call went out from the Alvarez's to say, look, we predict that we will find the fossil record will disappear instantaneously at these KT boundaries. If it's an impact, there should be no animals dying out prior to. There should be no extinctions leading up to. It should be the Earth as we know it, bang. Well, these are one of the animals, not the tiny planktonic creatures, but the animals themselves that were common in those Mesozoic seas And so the Alvarezes issued a challenge to the paleontologists. Go out and find your dinosaurs. Go out and find your ammonites or your clams or whatever you study and record the way in which they disappeared. Let us test the hypothesis that this was an impact that killed everything within a day or a month or a year instead of a long term. Ammonites themselves were beautiful organisms. This was the most common cephalopod of the sea. These fantastic chambered partitions would have given strength to the shell. There were more than 10,000 species of these in the Mesozoic oceans. They would have been more common than fish. It would have been fabulous to be swimming with these things. And then in a blink, or over a long period of time, depending if you were an impactor or a gradualist, they disappeared. So luckily for me, in 1981, 1982, 1983, I began working on a very beautiful set of cliffs in Spain. And finally, I finished in 1987 when the National Science Foundation said, that's enough. We know you never want to leave, but please stop. And so this is a fabulous place because the rocks themselves have been tilted up. They're lined up in such a fashion, and they're edge on. And on these big bedding plains, you can find lots of fossils. So you can count the strata, measure the strata, and recognize what was going on to this point. And this point, shown here in close-up, is a KT boundary. So the world changed so radically that the rocks themselves changed. Look at this. You've got this sort of pinkish rock here and then completely different set of rocks here. And the boundary between this turns out to be one of these millimeter-thick red layers. Wow. I mean, this is just catastrophe to a planet. So radically it changes the nature of rock formation. That's a good that's a good catastrophe. And so what we do with paleontologists is go out, and here's that rock now rendered into a stratigraphic section. We just measure its thickness, categorize it. Here's the KT boundary. Here's all the ammonites that were there. And sure enough, an awful lot of them went out here. But look, an awful lot of them are shown here. You could argue that there was a sudden catastrophe here, but what reasonable person would say, well, wait a minute, you had a lot of stuff dying out prior to it too. So, I mean, the Earth saw it coming. And what we paleontologists didn't know at the time is that when you collect fossils in this sort of fashion, you always get a curve like this. It became known as the Signor-Lipps curve because you can never get, in all probability, the last occurrence of anything. When you collect and collect and collect and collect, maybe you found this guy, and I'd gone 2 weeks later, I would have found another one up here. You just never know if that's the last one or not. How often does the fossil record give us a perfect fidelity picture of the ranges of species? And it turns out not very often and not very well. And that was one of the great lessons. But it led to a 10-year debate about was this a gradual extinction or a sudden extinction? And finally, some people started doing lots of good stats because there was lots of data sets like this and came to the recognition that the KT extinction was just a knife blade in the history of life. It was causing the river of life to do a 90-degree kink, and that kink happened in a day or a month or a year, which is how long it took to kill all that stuff. We now know where the crater is, the Chicxulub crater in through here. If it were in Texas, it would be up here, and I gave this lecture in Italy, and they kept yelling, "Where's the Bush Ranch?" And I said, oh, that's right up here. That's where the tidal wave level was back then. Because that's what happened. This thing hits. This is a shallow ocean, and we have tsunami wave deposits covering the entire Gulf region. I mean, this would have been kilometer-high waves picking up all those dinosaurs. What would a T-Rex do? Hang 3, right? Big crater. So big that nobody could really see it as a crater. This is that great Gary Larson cartoon where you're standing in this giant footprint. One paleontologist says to the other, I don't see anything, do you? No, I don't see anything. He lives near me, actually. He bought a third of Lake Washington and has this big waterfront estate and just quit. It's really sad. Big crater, we know it from geophysical size. This is the largest crater put on our planet in the last 500 million years. Well, that itself is interesting. These things don't happen often. Back in the history of life, they did. Recently, they do not. And that's going to be part of our story. Consequences. This is a nasty PowerPoint, but here's all the stuff that happens. Sunlight blocked for several months. Nitric acid. All the ecosystems would have been so perturbed because first, on the first few days, you have all this stuff falling back from space that lights up all of the forests and burns them down to the ground. And then you got darkness, and then you got change in temperature, and then you have lots of nasty dust in the air. It's just a mess. And yes, 50% of the species probably died out. So how does anything survive is the question. And the things that do survive are those that can burrow. So it would have been really good to be in a bomb shelter. If you could fly, you could get away from it. If you live deep in the ocean, that was a sure card for the lottery for success. But if you lived on the surface of the ocean, you were doomed. If you were large, you were doomed. And so many of the things that died out were plankton and things that lived in the shallow seas and big animals, poor dinosaurs. Now we need to jump to the Gaia hypothesis. Because we had in about 1970, just before this Alvarez impact hypothesis, before this idea that life improves the planet. So how in the world could impact be Gaian? Is it positive? Is it negative? Is it neutral? Well, the Gaians will say it's neutral. It's just one of these rare events that happens. But we need to bring Gaia up here because we're going to look at some other aspects of what kills things here. Extreme Gaia is the Earth itself is alive, and that's pseudoscience. But the Gaia hypothesis has produced an area of new science that really is good science. It's called Earth system science. It's examination of the carbon cycling, nitrogen, phosphorus, the elements that are all used for life. And these came directly out of this original Lovelock and later Margulis Gaia hypothesis. So at least in terms of the KT, we're left with a random act from space. It was external, it was unpredictable, and by 1990, very few people still opposed it. All of the evidence seemed to support rapid extinction. We understood why we had these supposed gradual extinctions. We had lots of evidence from the physical world. We had lots of geochemistry. And then the thought became, if one of the great mass extinctions was caused by impact, why not all? In 1995, I went to a conference where we were talking all about impacts, and there was some guy from Steve Spielberg there. I said, why would the movie people be interested in this? Well, soon thereafter, we have two movies, Deep Impact and Armageddon, which are direct results of the KT impact. They'd said, aha, asteroids. Impact became the dominant paradigm for all mass extinction on the planet. The problem is, though, from about 1995 and after, is that we began looking at some of the other big mass extinctions. And these, the biggest, are the PT, or the Permian Triassic extinction, and the TJ, the Triassic-Jurassic extinction. I want to look at these now in a little bit of detail, because both of these, in Science magazine separately, have been blamed on impact. The trouble is, as we geologists went out to look, we began to see that the evidence, this clear-cut disappearance of stuff, the iridium emplacement, these clay layers, these changed rocks, they don't look the same for these other mass extinctions. So what could cause, let's go back now, we're one of the old folks, what could the intrinsic, the in-earth extinction be? What could it possibly be that could cause rapid death of so many species? Because it wasn't just KT where we had a lot of things die out. Most recently, I'm convinced that this is a cause of intrinsic mass extinction, but if we get rid of this one and think about these, temperature change, something about the atmosphere, and somehow sea level, all three seem to be tied in perhaps to ways the stuff could die out. And the really big dilemma came about the year 2000 when it was found that one of the other big craters, the 100-kilometer Manicouagan crater, which is half the size of Chicxulub, dated at 214 million years ago. When enough paleontology was done, we could find the impact layer, and we found out that nothing died. So a 200-kilometer crater, half of all species go away, a 100-kilometer crater, and nothing dies. Increasingly now, science began to understand that perhaps it took giant impacts to do anything, and maybe half-giant impacts don't do anything at all. So let's look now at the two most interesting of the mass extinctions that haven't been as studied as this dinosaur-killing event. The first, the Permian extinction, also known as the Great Dying, or as Doug Irwin of the Smithsonian calls it, the mother of all mass extinctions, which makes me wonder who was the father. Common knowledge, highest extinction rate ever. Some people say 90% of all species. I wonder, though, in absolute numbers, that maybe it wasn't less than the KT because of that diversity curve. But this is heresy, right? Once the press gets it in its mind that it's the highest extinction rate, then you keep seeing that self-perpetuating. And secondly, was impact involved? And this brings to a really fascinating study published in 2001 in Science Magazine by a group led by Luann Becker, a geochemist, that there was an impact and that a whole new line of evidence needed to be brought out, the examination of what are called buckyballs. About the same time in 2000, I had been working in South Africa for 4 or 5 years because at the end of my National Science Foundation money to France, I couldn't go to France anymore. I had to go do something. And so I went to South Africa, and I was lucky enough to get there just as apartheid was disappearing. I began working there in 1991 and went back every year or twice a year till 2004. And this was the background for my book, Gorgon, a commercial word. And one of the areas we worked at was in a place called Lootsburg Pass. And providentially or not, some Boer family had died and left their gravestones right here on a Permian-Triassic boundary section. Buckyballs, Luann Becker used as evidence are these. These are mass spectrographs now of carbon compounds, and buckyballs are carbon 60s. And you get fragments of these in rock, and they can be 60s, and there's 120s peaks. And then these other peaks, these just tell you now, when you're looking at the rock, the weights of carbon that are present. Well, lots and lots of carbon 60s or 120s, or pieces therein, are pieces of what look like great big balls. And these balls are called buckyballs because their full name is carbon fullerenes. They have the shape of a geodesic dome of Buckminster Fuller, and hence that popular name. But Becker and her crew said it wasn't the buckyballs that were evidence so much, but the fact that within the buckyballs there was another marker for mass extinction by impact itself, something called helium-3. Helium-3 is found in great abundance in outer space. The hypothesis is that an impact hit the planet. The formation of that impact locked up and produced lots of these buckyballs, and in the middle of the buckyballs was sequestered extraterrestrial helium-3. And the presence of the buckyballs then was an indicator of impact. So in 2001, here's a whole new way, supposedly, to say that the Earth had been hit in the past. So a bunch of us went out and started looking for buckyballs. This is my own area in South Africa. This turns out to be the change between the Permian here and the Triassic, more rocks. In this particular case, however, we don't see that one layer. We see lots of thin layers. And it didn't look anything like a KT boundary layer. There wasn't one single layer. There wasn't any place you could say, well, that's it. There was no iridium. There's nothing. There's this gradual changeover. But nevertheless, buckyballs and its evidence was holding sway. Well, the work I was doing then changed from sea creatures to land creatures, and I want to show you a little bit about the world that did disappear about this time. This is the skull of a big mammal-like reptile called a Gorgonopsian. This would be about 1.5 meters. So we're looking at an animal that was probably about 9 feet long, probably low slung, had a tail that waggled back and forth, its arms were off to the side, and it would have looked a cross between a lion and a crocodile. So this is us, really, before we became the mammals that we are. This is the mammals that we were. And the world was filled with these things. And people say, hey, is that a dinosaur? No, this is way before dinosaurs. You get the cant that I learned is that you had this age of amphibians, which gave rise to the age of reptiles, and they were the dinosaurs, then the age of mammals. But the real world is that the mammals were there first, in huge numbers, because in all functional ways, these are essentially mammals. And it is this group that gets so cleaned out by this Permian extinction, whatever it was that happened. There's all kinds of them. This is my son, Patrick. This is definitely paleontological child abuse. Scale, be a scale, help! And around him we see there's big ones, and there's little ones, and there's all kinds of ones. But, you know, that's us and that's us. And the sad news about the world is that Permian extinction really stopped the age of mammals and brought about this age of dinosaurs, which is all a mistake anyway. There should never have been this age of dinosaurs, but for this Permian extinction. And I showed this. This is one of the last fossils I found. This is a pen for scale. It's still in the rock. And this is about the size of a robin head. And here you're looking really at yourself. This is the species in the lowest Triassic strata, after this mass extinction is over, that does give rise to all real mammals. So in the strata right below here, we have 50 species of these things and these things. And above we have 2 or 3, and this is one of them. And you can see the eye socket in here. Here's this little brain case. This is a little nose, and here's a little tooth. So it's about the size of a little tiny kitten, and would have looked something like a rat. And if that doesn't survive, we don't have this conversation, or something else has this conversation, but not us. So that's how close things got. We're down to 2 species of things after this gigantic Permian extinction. It was the mother of all mass extinctions. It was the worst in terms of how much life got strangled out of existence. And yet when we began looking at the nature of the record, and this is from work we published from our South African adventures for 10 years, and carbon isotope curves, and magnetostratigraphy, and putting together over a long period of time who appears and who disappears, it turns out that the creatures that come afterwards here, these are little error bars, seem to appear before these guys go extinct. It isn't the KT where it all dies out and new stuff appears. There's this big admixture of stuff going on. This is probably taking 20, 30, 40,000 years. Stuff's disappearing, stuff's reappearing. It's as if the Earth is going through maybe a 100,000-year interval of some sort of strange reorganization. And nowhere within it can we find evidence of impact. When we look on a longer time sense now, this can be over, we'll say, a 20 or 30 million year period. All the mammal-like reptiles of the Karoo Desert in South Africa put together. And this is what we call the Permian extinction, but there's a whole lot of stuff going out before it and a whole lot of stuff going out after it. So we're seeing a changeover from a mammal-like reptile world to what's taking place in here are the first dinosaur-like creatures, and eventually there's more and more dinosaurs. This changeover strangles whatever was here and replaces it with an entirely new and different world. It would be good to know what did that, and it would be good to know if it could ever happen again. So bizarre was this. I love this little PowerPoint. I was looking for squigglies, and here's PowerPoint. He even has its own. The rivers changed. The end of the Permian was covered with lots of meandering rivers. All rivers today meander, except in, say, places where you have clear-cut all of the trees away, or in deserts, or next to high glaciers. Then you get braided streams and braided rivers. Well, the Permian, the rivers were meandering, and then over about 10,000 years, they changed to all braided, the whole planet over. So Dave Montgomery at the University of Washington and I began looking for fossil evidence. What is the sedimological evidence of meandering river? We couldn't find any meandering rivers older than the Silurian in the planet's history. Why? Well, because it takes plants to stabilize banks, to give you the ability to have a meandering river. Until we had plants, all rivers on Earth were like this. If I were Chris Scheibe and looking for advanced life in outer space, all you'd have to do is image a faraway planet. If you saw this, you knew you had plants or plant equivalents. So life is extraordinarily important in the shape of the planet as we know it. The Permian extinction took us back to the time before plants so wiped out by whatever did this, re-evolve, and the rivers go back to meandering up through here. These mass extinction, folks, are gigantic, throttling strangulations of planet Earth. Alexis Rockman, my friend in New York City, painted this for me. Some stuff got through, Listersaurus, burrowing animals get through, but this is sort of our view, and I think it's probably a pretty good one. A world that has very little water taking place on it, at least in the middle of continents, no plants whatsoever, mammal-like reptiles dying, disappearing, going down the tubes. So let's go to the Jurassic extinction, the Triassic-Jurassic. The Permian was 250. We're going to go to 200 and look at one more evidence now of something thought to be impact that wasn't. Well, I should finish here with a buckyball story. One Luann Becker and her crew, go back, there. People went back and tried to replicate the results of the buckyballs, and no laboratory has ever been able to replicate these results, even from the same sample sites. So the buckyball hypothesis remains to be replicated, and unless there's replication, it's not science, or it's not science that can be verified. TJ, catastrophic. Paul Olson, nearby here in 2002, found evidence of iridium. Maybe it's one of these big impact extinctions. Big turnover taking place. Carbon dioxide, we know, was huge at that time, up to 2,000 parts per million. Right now it's 380. We had the emplacement of a gigantic flood basalt area. We had lots of methane going into the atmosphere. And I got to go see this in New Zealand a couple of years ago. One of the great joys of field geology is you get to go to great spots. So two of the sites we looked at trying to study this mass extinction, Frederick Island, British Columbia. This is a place you can only get to by helicopters. Vancouver Island is down through here. And what I didn't know is that this is a 200-inch per year rainforest, except it's not one of the warm rainforests. It's one of the cold rainforests. On one of the few sunny days. And the second place we worked on our rocks, this is in Nevada now, and in both of these places we looked again at mass extinctions, and in both places we found the same pattern as the Permian. There's not a layer with iridium. There's no impact extinction evidence whatsoever. Instead, what we do find in both places is this. This is a carbon isotope record now, taking place across this Triassic-Jurassic. A real quick lesson to carbon isotopes. Plants love CO2. They need it to stay alive, of course. And there's two types of carbon out there. There's carbon-12 and carbon-13. We've all heard of carbon-14, and that's certainly used for dating. But the two isotopes of 13 to 12 are very useful for studying the health of a planet. When you have a lot of photosynthesis taking place, plants preferentially take 12 out of the atmosphere. They leave 13 behind. And if you see then that there's changes in the ratio of 12 to 13, you can make inference about the amount of photosynthesis taking place. On these curves, when it goes this way, stuff's dying. When it goes this way, there's a lot of photosynthesis. Little life, lots of life. And when we began looking at these records across these boundaries, not only at the Triassic, but in the Permian too, we started finding these great big changes back and forth, a series of them. Well, the impact at the end of the Cretaceous just had a 1 negative and a positive, and life went on. In the Triassic, it goes negative, way positive, negative, positive. And the Permian does the same thing. The carbon isotope record indicates that it is not a single event across these other mass extinctions, but a series of perturbations of the carbon cycle itself that is equivalent in time to the extinctions. It's stretched out over 10,000 to 100,000 to 1 million years. And we find not only the record of carbon isotopes, these are the records of pieces of bacteria. They're called biomarkers. And in rock, you can get very interesting bits of lipid cell wall that are specific to particular bacterial groups. And what we find across this is that right in through here, a huge amount of biomarkers of hydrogen sulfide oxidizing bacteria. Bacteria that can only live if a large amount of hydrogen sulfide is present. Anybody here have chemistry with H2S labs? Before they took it away, I did. You come home, smell like rotten eggs. Hydrogen sulfide is a hideous poison. The evidence by 2003 was that at the Triassic-Jurassic boundary, in 2005 at the Permian-Triassic boundary, that biomarkers indicate the world's oceans filled with hydrogen sulfide. There's no other way to explain these observations. Which led in 2005 to the Kump et al. Hypothesis, which is the scariest of the mass extinction ideas, and it indicates to me if there were a designer, he was a very malicious soul. The Kump hypothesis is there's a buildup of hydrogen sulfide on low oxygen bottoms, and that these bloom sufficiently to trigger the release of the gas, which is in solution. If there's enough of it, it goes out of solution into the ocean and into the atmosphere. H2S poisoning is a kill mechanism in two ways. At 200 parts per million, it will kill any animal. And at the same time, that level, that concentration will cause the ozone in our atmosphere to disappear. So we lose our ozone layer and we have H2S into the atmosphere. And this is now recorded evidence from both the Triassic, Jurassic, and the Permian Triassic from various lines of evidence. This looks to be a much better indicator as an explanation of the mass extinctions, all except the KT, than anything else we've looked at. In fact, we now have evidence that more than 10 of the big and the little mass extinctions were caused by 10,000 to 100,000 year intervals when hydrogen sulfide is being vented into the atmosphere through bacterial explosions. So how do you test this? And you test it by the biomarkers, and isoronurethane is the biomarker that is indicative of hydrogen sulfide bacteria. These are blue and purple sulfur bacteria. And when they occur in sufficient presence, when they die onto the bottom, they leave pieces of their cell wall, and we find this particular carbon compound. So finally, let's look at one last mass extinction, which is really a key to the present day, which is where I want to get to. The end Paleocene event, another one of these strange non-impact, but lots of stuff died. But because this one was only 60 million years ago, we can have a lot better indication from fresher rocks and younger rocks about what happened. And what happened here is that oceanographers in 1991 began to see that we had a period when the oceans seemed to go from lots of oxygen on the bottom to no oxygen on the bottom. And at the same time, there was indication of an enormous amount of carbon dioxide going into the atmosphere, volcanic carbon dioxide. And what happens in this is that when the Arctic gets warm and the tropics are warm, you don't have the push for currents. I mean, what causes our planet now to have wind currents and ocean currents and all these big bad storms is you have a warm tropics and a cool Arctic. But if you warm the Arctic, if you reduce that temperature gradient, your currents slow down. Everything slows down. The thermal circulation pattern that now carries warm surface and cold oxygenated water stops. And when that happens, the oceans go anoxic. And when they go anoxic, you bloom these bacteria. The change caused by short-term global warming is volcanic in the past. It leads to circulation change, and that causes more warming. And so we really start seeing that the past is a time of ocean states, and I suspect it is these ocean state changes that are correlated with the great disasters of the past. Impact can cause extinction, but it did so in our past only once that we can tell, whereas this has happened over and over and over again. We have 15 times of mass extinction in the past 500 million years. So the implications, what are the implications? The implications are that carbon dioxide is really dangerous. If you heat your planet sufficiently to cause your Arctic to melt, if you cause the temperature gradient between your tropics and your Arctic to be reduced, you risk going back to a state that produces these hydrogen sulfide pulses. It's not only carbon dioxide which has gone up and down through time. This is the carbon dioxide curve here. And the strange, odd thing now is that we're almost out of it. The real irony is that if you show up tomorrow night after I've tortured you tonight, we're going to see that this is the reason, or will be the reason, for the end of animals on our planet. We're going to run out of carbon dioxide. It's going to cause plants to disappear. That's the 500 million year limit I told you about. But carbon dioxide and oxygen are in opposition. This is from Robert Berner at Yale. When CO2 has been high, oxygen has been low. When carbon dioxide has crashed in the past, oxygen levels have gone up. And in fact, this up-down of carbon dioxide and oxygen can also be related back to these mass extinctions. Here's the oxygen curve from Bob Berner, and these red lines now are these mass extinctions that are associated with the hydrogen sulfide bursts. And they all seem to happen at times when oxygen levels drop, and oxygen levels drop when the world gets very warm. Our oxygen and our carbon dioxide are in opposition. So where does that leave us? It leaves us in a planet where oxygen can go up and go down. This is a map of the world today, but it's also a map of contours, because at the end of the Permian, not only was oxygen high, carbon dioxide high, oxygen levels were so low that any area in red here would have been at altitude too high for an animal to live. At the end of the Permian, the oxygen levels were so low it would have been equivalent to 14,000 feet. So we don't have a stable planet. CO2 goes up, oxygen goes down. When oxygen goes down, animal life gets distributed at ever narrower coastal areas at sea level. And the main cause of this in the past has been these. These are big red basalt layers. And we can think of it like this. Each of these is called a flood basalt. They take place over fairly short periods of time. And they're the final piece of this puzzle, and I'm almost through. Why did we have these clump episodes? We had them because one of these things happens. A huge amount of basalt comes out for whatever reason. I mean, that's the mystery. And covers a gigantic surface of the planet. And in so doing, huge amounts of carbon dioxide come out. Someone asked after the Scientific American article, why don't everything die off? Well, because these things are limited. They come to a certain size and they stop. And when they stop, carbon dioxide drops. And when it drops, the Earth starts using up the carbon dioxide in the atmosphere. It starts getting colder in the pole. Circulation starts increasing. The oceans get oxygenated, crisis over. The amount of extinction, the size of the extinction is directly related to how much lava poured out, bringing carbon dioxide out with it. Well, that's well and good if carbon dioxide were only being produced by volcanoes, but it's not. It's being produced by human industry. Can the CO2 we are producing in any way, shape, or form be matched up to the rates of change that happen in these mass extinctions? That's the current challenge. Let's hope not. But in all probability, it is. These are the levels now, this is a brand new graph, of carbon dioxide through time in parts per million. And here we are today, right there. So at each of these reds are when we had these nasty global warming extinctions. The last one is right here. There's about 700 parts per million. We are here, we're projected to be here, if not by the end of this century, certainly by the end of next century. And this is way over the critical threshold point at which we can start seeing the same processes happen again. So it's not the volcanoes, it's us. The new view is that carbon dioxide is the most dangerous part of this planet and the most important part of the planet. Got to have it for the plants. Too much of a good thing kills the planet and its biota. Stagnant oceans go biotic. Emission of hydrogen sulfide goes to the atmosphere when you get these bacteria blooming. Loss of ozone, direct poisoning, dead stuff. It's happened 15 times in the past. Can it happen again? It's happening right now. How fast? How fast do we get to 1,000 ppm? The tipping point is 500. After 500, all bets are off. That's misspelled. Piss poor design? Who wrote that? Okay, so here's my answer to the Gaia hypothesis, Medea hypothesis. She murders her children. This isn't some new age wonderful mother goddess out there suckering life and letting it make everything better. It's a hard, cold, nasty, cruel planet. All planets are hard, cold, nasty. They don't care if we're alive or not. Life itself is probably inherently suicidal, and I can give you 10 episodes from the geological record to show this. Snowball Earth, various glaciations, the oxygen poisoning events. Things just don't care. It's not that way. Things grow and they die. Planetary conditions will ultimately kill us. There's only one way out, and that's intelligence. And the point of view I'm taking now, and I hate this resolution. I hope I'm totally, absolutely wrong. I want the Earth to go back to this wonderful green place, all the humans and all our workings and I can go get a beer afterwards and everything, and yet nature is perfectly there and green, there's no freeways and all that stuff. But if we go back that way, we're going to die. And if we want to live, we're going to have to bioengineer on a gigantic scale. We're going to have to engineer this planet with planet-wide engineering. That's the only way out. And eventually we will have to get out, even after all that. And I'm going to talk about that on the last night, what hope is and what it's going to require. So Medea hypothesis isn't quite so hopeful, but there's somewhat liberating to me in that no designer did it. Thank you. I'll take as many questions as you have the patience for. If you want to leave, go.
So there are 2 microphones, I believe, in the back of the room. And if you'd like to ask a question, wait for the mic to come to you. And we'll take them for about 15 minutes.
Good.
Up to 15 minutes, or less.
I'm here. I'm yours.
Question.
Yeah.
Were the volcanic events accompanied by substantial emission of sulfur into the atmosphere from volcanoes?
Yeah, there's a lot of sulfur going into the atmosphere from volcanoes. Yeah, the question is, if I get this question, there is currently a lot of sulfur going into the atmosphere through volcanoes. Is that the correct question? And it's not doing anything to us?
No, the point was, if the volcanoes added at those phases a lot of CO2, did they also add a lot of sulfur leading directly to poisoning?
Yes, there's a tremendous amount of sulfur going up, but the sulfur coming out isn't poisonous. Not as poisonous as hydrogen sulfide. Hydrogen sulfide is deadly poisonous to any animal. Look, the real glib answer to all of our problems, if we could find the switch and turn off the volcanoes, we can drive all the SUVs we ever want. It's not just humans. It's all the volcanic stuff that keeps going. But we can't do that. We are definitely heading towards what in the past has been a big problem.
Is the preponderance of evidence that these volcanic eruptions were random? You had some super Krakatoa going off in a few places, or is there some indication that some kind of Earth-wide volcanic cycle, that it's some kind of process causes a whole bunch of volcanoes to erupt in a relatively short time?
Yeah, well, using volcanic is a misnomer. When I think of volcano, I think of a big explosion. Flood basalts are basically different. Flood basalts, there's no cone. There's not a big, tall chimney volcano like we know. Eastern Washington State. Well, you don't have to go very far. All around here, the Palisades. You see these gigantic lava areas where huge amounts of volcanoes have come out. The entire Connecticut River Valley is underlaid by basalt. All you have to do is go along the Hudson River, and you got the Palisades Park and all those gigantic stacks of volcanic material. That's Triassic, Jurassic in age. That caused the Triassic, Jurassic mass extinction. These things aren't boom. These are just slow bubbling out of lava that cover enormous areas. The largest flood basalt on the planet is exactly end Permian age, totally coincident with the mass extinction. It's in Siberia, called the Siberian Traps. It takes about 1/4 of the land area of Siberia. I mean, this is bigger than the continental United States if you look at this overall massive size. That much volcanic material coming out over 1 million to 2 million years. The volume of carbon dioxide can be estimated, and it raised the CO2 level in the Permian from 2,000 to 6,000 parts per million. We have the highest CO2 in the Phanerozoic with the biggest mass extinction. The estimated CO2, the percent species going out are highly correlated. Now, it's not how much CO2 comes out, it's how much comes out over a given interval time, too, because carbon dioxide is being taken out of the atmosphere. We form coral reefs. We have plants that are weathering. We have all kinds of ways of taking carbon dioxide, and we can make living plants, we can make carbonates, we can do all kinds of stuff with it. I mean, our big problem with carbon dioxide is that too much is being tied up in limestone, and plate tectonics is then sequestering those limestones onto the continents, and we can't dissolve them out. Humans are going to have to start making carbon dioxide to survive on this planet over the next few hundreds of millions of years, but we have to get through the next 1,000. Question in the back. Exactly. The Deccan traps. And this is the hardest to understand because we don't see much of an impact and effect of the Deccan. There is a big flood basalt, but the deccan seems to be distributed over more millions of years than we have these others. Again, it's not how big it is, it's how fast does it come out per unit time, and that seems to have been a slow bubbler. But this is used, as you know, by the opponents to impact for years to say there is no KT impact. And so it is a great valid point that people like me are still uncomfortable with. I mean, what did deccan do? And again, the new information seems to be that deccan was a lot of stuff, but over a very long period of time, unlike Siberian, which is a lot of stuff in a short period of time. In the front, please. I'll just repeat the question.
Because we have cable viewers.
Cable viewers.
There are species which die not because of catastrophic or mass extinction as you were describing tonight. Now, they just die out of evolution. What does theory of evolution say why species evolve themselves out of existence?
David Raup approached that question with the title of a book. He said, Extinction, Bad Genes, or Bad Luck. And their thinking is that if you have so many different species, there are times when you can roll the dice and they die. But the species that die most readily, unfortunately, the species we love most. Rare species, rare birds, birds on islands. Island birds are the most susceptible to extinction of anything on the planet. Flightless birds on islands that humans come to, are hungry humans come to, are the most susceptible to extinction. Again, if you have wide distribution, you're not going to die off as readily. If you can distribute yourself out of problems way, you're not going to die off. I mean, when we have smaller, simpler things, right now we wish we could date the ranges of bacteria. We wish there were certainly more morphologies in bacteria to know. I think some of these bacterial species are billions of years in age.
But that seems just to beg the question, why some species become so rare then?
Some species become so incredibly narrow in their food tolerance or their temperature tolerance. Now, a really good example is in Hawaii. Hawaii had a series of geese get to it. The geese evolved into flightless forms because there were no mammals on Hawaii, no predators at all. And they became extremely narrowly adapted to one type of plant food. The Hawaiians did two things. The Hawaiians ate the flightless geese, but they caused about 40 other species to go extinct, not by killing the birds at all, but by making taro fields. When they changed local native Hawaiian plant vegetation to agricultural fields, it resulted in 10 to 20 to 30 species going out because those species could not take any sort of perturbation, narrowly adapted. I don't think I'm answering your question. I'm trying. Question, please.
In general, changing the distribution of animal, and I was wondering if that idea is backed up by fossil founding?
We know so much more about carbon dioxide levels through time than we do oxygen, because you can make a direct read on CO2. You do it in two ways. You can do carbon isotopes of carbonate nodules that are formed in non-marine environments, but the best way, look at fossil leaves. They have tiny holes that let carbon dioxide in or out. And you can grow a leaf in high CO2, and it'll produce a few tiny of those holes. In low CO2, it has lots. It needs it. The fossil record tells us CO2. Oxygen through time is much harder. Robert Berner at Yale does it best. But we've found a lot of really good indication that his curves are correct. Berner predicted that the highest oxygen in the last 500 million years was 300 million years ago, and that's the time when we find the biggest insects ever on the planet. Large insects could only exist because of really bad respiratory systems under high oxygen conditions.
But if there was such, excuse me, you use the microphone.
If there was such towards other parts of the area of the planet, you should find them in fossil. On that.
Oh, I see what you mean. You're talking about elevation.
Yeah.
Yeah. At the end of the Permian, the calculations are that almost everything had to be at sea level. And if you even go up to 5,000 feet, you're not going to find very much in the way of life. The trouble is the sedimentary record preserves almost always basins that are at sea level or near it. Mountains just don't preserve. So we don't have a really good measure of paleo elevation. We can't take a rock measure and say this is 7,000 feet. We can just make predictions based on oxygen levels probably what the oxygen levels were at any given altitude. Question right in front.
I'd like to return to intelligent design for a moment. It would seem to me that one of the arguments could be that the improbability of our existence based upon the fact that if several fundamental physical constants were slightly different, we would not be here. And I'd like you to comment on that, please.
Yeah, I certainly would do that in Lecture 3, the anthropic principle, and I'm going to comment on that in greater detail then, although I'm no physicist, and I'm just going to parrot what I read. You're totally correct, and the idea perhaps is that there are multiverses and that we are the one of the multi where life could exist, and that you have all these other universes where life doesn't exist because those constants are different. But that's so hairy-fairy to me.
Just a casual question. You just say that life is inherently suicidal. What do you mean by that? I mean, I can understand that our species is trying to kill itself by driving SUVs or whatever, but does life generally do that?
Well, it's not consciously suicidal, but my sense is, I thought a lot about species. What does a species want to do? And I think any species wants to become as widespread, as abundant as it possibly can. And no species worries any bit at all about other species. I mean, if you put two beetles in a jar and they have one particular food source, they're both going to eat themselves out of existence without worrying about it. Species don't do conservation. There's no altruism in nature that I can see. It takes intelligence for real altruism. And in this particular case, I think maybe it's a very cynical point of view, but I don't think that the fact we have so much diversity isn't by any sort of effect of species knowing that a diverse world is greater than a non-diverse world. It's by natural processes producing that. But it's certainly not from any species saying, I don't want to take over the world. Because look what we did, we humans. I mean, we distribute as far as we can. Will we ever stop population numbers? What are we at, 6 billion now? What's this world going to be like when we hit 9 billion by the end of the century?
But evolution may be ruthless, but it's ultimately for the improvement of life in general, isn't it? In quality and complexity.
I don't know. Question, please. Methane.
Supposedly there's a huge reservoir of methane in the oceans, and it does impact on the possibility of fuel and increase of carbon dioxide through using it.
Yeah, you're absolutely correct. There's a lot of methane frozen called clathrates, and a clathrate is a gas hydrate. It's just simply frozen methane, CH4. If you unfreeze it, it becomes a gas, and it can move into the atmosphere, and methane is a far more efficient greenhouse gas than carbon dioxide is. But methane converts to carbon dioxide 20 to 40 years in the atmosphere. It's hit by sunlight, it reacts with oxygen, and it actually, to produce carbon dioxide out of methane, it starts grabbing oxygen to do that. And so methane is a scarier, more dangerous gas than carbon dioxide even. And so the trouble with methane is, as we warm the Arctic, we are releasing methane from frozen clathrates. And the warmer it gets, the farther north they unfreeze, which makes it warm enough to go a little farther. And so it's one of these events that perpetuates themselves, runaway. Question?
I really enjoyed the lecture, but I was kind of, I had a problem.
Really enjoy the lecture? When but is the fifth word, you're in real trouble.
Exactly. But I was having trouble following the logic, of the connection between these facts you presented us tonight and the Medea hypothesis that life is suicidal and planets are barren. I mean, it seems like it's just as gratuitous to say, that life doesn't care or that the universe doesn't care as that it does. I was looking at one of your slides. One of the questions you bring up is that it's it's hard to find a criterion of success for a species. And and you go on to say that, all these terrible mass extinctions happen, and that, maybe the good of the species is to expand as much as possible, but then you turn around and say that it's not a good thing for a species like us to expand as much as possible. So it just seems like you shift the standard of values. Like at some points you say that it might be good for this life to survive. So like you mentioned your falsification criterion for accepting or rejecting evolution. I wonder if you have a similar criterion for the kind of cosmic pessimism you put forward at the end there. I mean, what level of design would be perfect enough? Because it seems like the one that would be perfect for us might be really, really bad for other forms of life.
Well, I'm even more confused than you make me out to be. That's the scary part. No, you great points. I personally have come up with what may have seemed like a rather cynical point of view about how I interpret the facts, but any lecture is the facts and then one's interpretation. That's what science is too. So, okay, I mean, I will be mea culpa. I could have done better, but you get what you pay for too. We talk afterwards. Another question. If there's no more questions.
Peter, I wanted to take the liberty of taking this break to ask you a question myself. I wanted to follow up on this question a little bit with this Medea hypothesis. And you've talked so far about catastrophes that lead to large geological changes. And you've also talked about natural selection acting to improve fitness and increase spread of a species. Now, to tie this in with this idea of intelligence as being a way to save us, as it were, from global warming, I wonder whether a more neutral explanation would be just that intelligence acts as something that amplifies natural processes. So, for instance, in the sense that one can breed dogs over short periods of time to change much more quickly than selection produces new dogs. Could one interpret intelligence as being something that can, say, take the natural effect of something such as a fire and then convert it to large-scale changes in carbon dioxide? And so rather than take a particular view about life or anything as being intrinsic, to think of intelligence as being something that amplifies natural effects. And since we don't, at a micro level, understand what the effects of these are going to be, we're the beagles in a jar, wherever you got that analogy from, that intelligence basically, that species act to amplify, and it's not, and they act in a very limited range and don't take the view of understanding what will happen when that is taken to an extreme.
Yeah, the point about intelligence, too, is that there's a lot of people, the SETI Institute, as you know, worries an awful lot about intelligence. And what is intelligence? And I don't mean to belittle your question at all. And I wish if it were written down, I could hear it again when I'm not, after you give an hour lecture, my IQ is about 7 now or 12 or something. But, I mean, you have some great points. You pick and choose. And picking and choosing, I think, is definitely what even intelligence does. I mean, what we humans are doing is we cherry pick. We cherry pick in terms of analyzing things, and we cherry pick certainly technologically and what we are going to use and not use. In terms of the overall engineering, I listen to my friend Don Brownlee a lot, and he is really struck with the idea that the only way to get back at global warming eventually will be big panels in space. He wants to put big mylar up there and block the sun. And I seem like that's so idiotic. Why don't we just do some conservation on Earth? But he's far more cynical than I am. He said it won't happen. And his point of view is that when China and India all have cars, when the standard of living raises to the point where the number of automobiles on this planet goes, say, 5 times what it is now, then whatever the United States does is irrelevant. I hate that. I mean, I hate that. I hate that so much because that means, well, then if it's irrelevant, we don't have to do anything. And that argument becomes self-perpetuating on a global scale. Well, China says, well, India's not going to do it, so I'm not going to do it. And then we get to the point where Brownlee may be correct, that it gets to the point where the humans on the ground can't do anything anymore, and you're going to do a mega engineering. And so I'm really struck by the fact that you read popular science or popular mechanics, you will see all kinds of these really crackpot, strange ideas. But from those come these mega engineering projects that may actually work. The strangest, stupidest one I ever heard, as we're going to see if any of you dare show up, or I mean, if it's empty tomorrow night, that's maybe I understood what a bad lecture it was tonight. But our Earth is going to get too hot. Our sun is going to expand. And as that happens, we either move to a different planet or we move the Earth. Well, moving the Earth is actually practical, and somebody in popular mechanics came up with an idea how to do it. You go to the asteroid belt and you throw, I think it was 10 million large-sized asteroids and just miss the Earth. And when it comes really close, each time it jerks the Earth away from the sun a little bit. So we have to have a government project where if you screw up one time, you obliterate all life on the planet. But I mean, that's the sort of level of engineering, that we couldn't do now. But if you could get to that level, you could do this sort of stuff. I mean, we talk about big engineering now. I think about all the stuff I've seen in my lifetime that always goes bad. But, we would have to be sort of the next evolutionary step up in great engineering.
That would definitely be a federal level project. Okay, well, Peter, thanks very much.